In this section, we're going to start taking a look at just a basic overview as to what a differential equation is, and just some really basic methods to be able to verify, solve, and then finally what a differential equation, what the graph of one of these differentials might look like, both the solutions as well as the differential equation itself. All right, so some really basic terminology. So what is a differential equation? Well, it's any equation that contains a derivative and its solution is an unknown function, right? And it might have more than one derivative in it. So we might have like second order, third order, etc. Solution is going to be a function or even a family of functions that satisfies a differential equation. And what we could do is we could just substitute that function and its derivatives back into the original differential equation to determine if it's going to be a solution. And we'll see examples of this. The order is the number of derivatives, or the highest derivative in the equation. A differential equation may have a family of solutions, and we'll see an example of that in a few moments. An initial value is going to be some value that tells us the point or a point that falls on a curve that is a specific member of a family of solutions. And again, we'll see that in a moment when we take a look at a picture of both a family and a single solution. The general solution is going to be that family. Okay, so it's basically going to be all the possible solutions of a differential equation. And then finally, a particular solution is going to be one member of the family, and it passes through the point given by the initial value. So a really easy way to explain this, all right? Consider this basic differential equation. F prime is equal to 2x. And we know the antiderivative of that is going to be x squared, but plus a constant c, okay? Because we know if we take the derivative of c, the derivative of a constant is 0. So that just gets us back to this f prime, okay? So what we're going to do is we're going to just say, okay, well, these are all parabolas, all right? So when we graph those, we get this family of functions. So this is just some of the members of the family, okay? So all of these parabolas. But of course, there's more than that, right? There's a parabola right here if we were to graph it, and there would be one right here if we were to graph it, but we just don't do it because then it would just get really cluttered, okay? So we just graph a few of them just out of convenience. A single member of this family would be at the point 0, 1, all right? And so that's a particular value, x squared plus 1, all right? So that's going to be like the particular solution, all right? So notice that the particular solution is a single member of the family of solutions, all right? So that's what a differential equation is, okay? So it just contains a derivative or more than one derivative. And then what we could do is we could just take the antiderivative to be able to undo that, to be able to solve a differential. And that's going to give us a family of solutions. So let's take a look at some examples first, where we just verify whether a solution satisfies a differential. And to do that, what we're going to do is we're just going to find the derivatives necessary to substitute back into the original differential equation. Okay, so a really basic example. So this is our differential equation, y prime plus y equals sine x. And the solution, or the proposed solution, is 1/2 sine x minus 1/2 cos x plus 10 e to the minus x. So let's find the derivative of that first, because we notice that we can easily substitute y back in, but we need the derivative to substitute y prime. So we know the derivative of sine is cos. We know that the derivative of cos is negative sine, so that's going to turn into a plus 1/2 sine x. And using our chain rule, we're going to have negative 10 e to the minus x as the derivative to 10 e to the minus x. And so what we're going to do is we're going to substitute this back in to y prime. We're going to substitute this back into y, and we're going to see if it equals when we simplify sine of x. All right, so substituting, that gives us 1/2 cos x plus 1/2 sine x minus 10 e to the minus x. All right, so that's just going to be for y prime. And then for y, we're going to say plus 1/2 sine x minus 1/2 cos x plus 10 e to the minus x, and that's supposed to be equal to sine of x. Okay, so notice I just substituted back in for both of those. Now, if we go through and simplify, notice we have 1/2 cos and minus 1/2 cos. Those cancel out. Notice that we have negative 10 e to the minus x and positive 10 e to the minus x. Those cancel out. And then we have a half plus a half, which is going to be 1 sine x, and that clearly does equal sine x. Okay, so again, all we're doing is we're just substituting once we find the derivative or derivatives back into the original differential. So again, y prime goes here and y goes right here. And then we just simplify by doing some addition, some combining like terms. Another example, we have our derivative dy dx equals 25 plus y squared, and y is going to be 5 tan 5x. All right, so that means we need dy dx, which is just the derivative. And using our chain rule, that's going to be 25. So we take a derivative of 5 inside of there. Derivative of tangent is secant square of 5x. And so we're just going to substitute dy dx back in here. We're going to substitute y back in here. And so that gives us 25 sec square of 5x equals 25 plus the quantity of 5 tan 5x squared. Now, let's simplify the right-hand side. So this becomes 25 plus 25 tan of 5x, or tan square 5x, excuse me. We can factor out a 25, and we would be left with 1 plus tan square of 5x. And you probably remember that 1 plus tan square of x is going to be equal to sec square of x. So that would imply that 1 plus tan square of 5x is going to be equal to sec square of 5x. Okay, so we just change the interior angle there. And so we would get that this is going to be equal to 25 times sec square of 5x, which is precisely the left-hand side, 25 sec square of 5x. And so it is valid. Okay. One last example, and this one, we have a second derivative. So we have f double prime of t plus f prime of t minus 12ft equals 0. And f at t is c1 e to the 3t, c2 e to the minus 4t. So this time we're going to have to find two derivatives, and it's actually going to get a little bit long, okay, but it won't be too bad. So first derivative is going to be 3c1 e to the 3t minus 4c2 e to the minus 4t. All right, so c1 is like a constant, like a 7 or a pi or something like that. And so we just use our chain rule and move the 3 in front of it. All right, so for the second derivative, we're going to use another chain rule. That's going to be 9c1 e to the 3t. Negative 4 and negative 4 is going to be plus 16c2 e to the minus 4t. And now we're just going to substitute all of these back in. Okay, so we're going to substitute, we're going to substitute, and we're going to substitute. Okay, so the dE now becomes, we're going to take the second derivative. All right, so it's going to be 9c1 e to the 3t plus 16c2 e to the minus 4t. All right, so that's for f prime, or f double prime, excuse me. Then we're going to add f prime, which is 3c1 e to the 3t minus 4c2 e to the minus 4t. And then finally, we get minus 12 of the original function. All right, so that's minus 12 c1 e to the 3t minus 12 c2 e to the minus 4t. All right, and that should be equal to 0. Okay, we're going to hope. Okay, so that's minus 4t e to the minus 4t equals 0. All right, so let's see if that works out. So we have 9 and 3. So this is going to be a positive 12 e to the 3t. But then down here we have a minus 12 c1 e to the minus 3t. So this, and this are all going to cancel out. Over here, we have positive 16 minus 4. All right, so that's going to be 12c2 e to the minus 4t. But then we have a minus 12c2 e to the minus 4t. So those cancel out as well. And so what we end up with is the profound statement that 0 equals 0. And so indeed, it does satisfy. All right, so one of the very first things that we need to do with differentials is if you're given the solution to be able to check the solution. So again, you just find the derivatives, and then once you find those derivatives, you substitute back into the original differential, and then you just combine like terms. All right. So in the next examples, what we're going to do is we're going to learn how do we solve some really elementary sorts of differential equations.